Hi everyone. Thanks for continuing to tag along in this introduction to R and all the applications that we can use it for in finance. This week's video is really just going to be a slight extension on last week's video where I walked us through how to plot the capital allocation line. So this week's video is going to extend on that just a little bit by repeating a lot of the info from last week, but we're also going to plot the efficient frontier and optimize the two asset portfolio. Well, with that said, the first half of this script, or really a little bit over half of this script, is really just a repeat of things that you've already seen. So what we're going to do is use the same 5 functions as before: the Yahoo Finance package, the tidyverse, Lubridate. We could use SQLDF if we wanted to, and we're also going to use the ReadXL library. I believe for the SQLDF code, I don't have any specific uses for it in this particular script. However, it really would not be difficult for us to incorporate it. But anywho, let's jump right in, and will um, I'll just do a quick review, and then we'll incorporate the new stuff with the optimization aspects. Well, first thing we need to do is set a working directory. Remember, this is just a way to tell R around which files within File Explorer or within the Finder system on a Mac we're going to be working around. So here, telling R I'm going to be working within my OneDrive file, within a folder related to classes that I've taught, the specific semester, and the class. But this could be anything. Remember last week, in order to call index data from the S&P 500, remember to call data from Yahoo Finance, I needed to use the index function within the Yahoo Finance data. And what this says is R is going to call data related to an index, specifically the GSPC or the S&P 500 index within Yahoo Finance, and then I will call this call the S&P 500 call objects. This next step is the specific step in which I obtain my data related to the S&P 500, and I go from 1999 to 2020, but really the main data that I care about is from 2000 to 2020. So I include just one extra month of data because I'm going to ultimately want to lag my observations to be able to get returns across the whole time series that I care about. This next step is just a bunch of manipulation. The pipe operator allows us to combine multiple steps into one. The first object I call within the sequence of steps is the data frame that I am basing all of my manipulations upon. And because I don't want to change my raw data, but rather I want to manipulate it and then save it in a new form, that's why I say, hey, my new object is SP500. It's going to be equal to some old data that's been manipulated, and then I'm going to remove all the extraneous variables that I no longer care about. Now notice everything within this mutate step is something that we've talked about in a previous video, where my date column, I want it to be just dates without any sort of timestamp on it. Then I want to identify the month and the year of my observation. I want to identify a month no just in case I need to use SQL for anything. Then I'm going to use a lag function to identify the previous close value. But recall, this is useful only whenever I have a full time series, meaning there's no gaps in my observations. And then my HPR variable is just a way to get my return, right? It's the same thing as like a new minus old divided by old value, which you've probably learned from like Algebra 1 or Algebra 2 back in high school. Run this stuff, then I can aggregate my data, my monthly data up to a yearly aggregation by taking the data, grouping it by year, and then computing a geometric mean of the returns and computing the standard deviation or the volatility of all the returns. And just to refresh ourselves of this data, you'll notice a couple things. So first, for each observation from years 2000 to 2020, I have 12 observations, which implies I have a full time series of S&P 500 data within each year. But then in 1999, I don't have a populated value for the S&P 500's volatility. I do have something for return, but that's just because R essentially just took an average of one value. I don't care about this, the first observation, so we'll just ignore it for now. I want to add my risk-free rates though into this yearly data set. So I'll do a left join and then I'll compute the excess returns for each year within my time series. Now notice my NAs have been extended because there's no risk-free rate in my raw my RF rates dataset, and excess returns because its value depends on the RF rate column is now also an NA. Now my next step, if you recall from the previous video, I used to generate some assumptions about the expected returns on a portfolio. In that video, I assume the year I care about is 2019, but you can make your assumptions based off of anything. I then would generate some expected portfolio returns for each given level of risk. Previously, I cared about values that were linear combinations of a risk-free and a risky allocation of a portfolio that ranged from 1% to 100% in each of the respective assets. Here, I've consolidated it down into 10% buckets, but the idea is the same. So my portfolio returns column is just going to be a linear combination of each of the weights multiplied by the expected return on the S&P 500 in 2019 and the risk-free rate in 2019. Likewise, the portfolio volatility is going to be a linear combination or just a product of the weights that this portfolio has in equity times the volatility. And the reason that is because this is a complete portfolio comprised of a risky and a risk-free asset. The excess returns is just the returns for the portfolio less the risk-free rate, and then the Sharpe ratio is the excess returns divided by the volatility. The Sharpe ratio is the same for each observation here, simply because this is ultimately the capital allocation line, which just tells us the relationship between expected returns, the third column here, and portfolio volatility. This makes a little more sense whenever we plot the capital allocation line using the ggplot set of functions in a scatter plots. That's what GM point represents. If we zoom in, we can see on the x-axis we have portfolio volatility, and on the y-axis we have the expected returns of a portfolio. And what this tells us is within this framework of a risky and a risk-free asset comprising the complete portfolio, there's a linear relationship between the expected returns that we could generate and the expected portfolio volatility. And all it tells us is we can reach a higher level of returns at the cost of greater volatility. So if you are not okay with a higher volatility portfolio, that's okay. Nothing wrong with that. You can lower the volatility, but it's going to be less risky, which means you're going to get a lower return. Now recall in finance, we have this key idea where the more risk something has, the greater the expected returns. And that's what the capital allocation line tells us. So that's really just a quick recap of everything we did last week. Now, what I want to do is now optimize a 2-asset risky portfolio. So we're already assuming that you're going to have some risk-free asset. You're going to be investing in treasuries. However, now what you want to do is optimize the risky portion of your portfolio. This could be between bonds and equities. It could be derivatives and cryptocurrencies. It could be bond funds for municipalities and bond funds for corporations. It doesn't matter, just so long as we have 2 risky assets. As is tradition with a lot of stuff I do, my 2 assets are going to include an S&P 500 fund and something else. Now, what I want to do is collect data from Yahoo Finance again, but instead of calling an index, I want an actual asset, right? Because you can't buy SP 500. You have to buy some asset that tracks the S&P 500, which the asset that I'm going to use is SPY, which is the SPDR ETF, and it pretty much tracks the S&P 500 to a T. And as before, we're going to have to call the data from S&P 500, but instead of using index, we're going to use ticker. So I will control enter this to run the data, and I'm going to repeat pretty much the same command as I use for the index, but instead of using the index call, I will use the SPY call that I just defined up here over the same time series, just to make things equivalent. And now I'm going to just repeat what I've done before, where this is pretty much copy and pasted from above, but now I'm using the SPY data as my raw data, and I'm going to manipulate it to get my holding period returns, or my month-to-month returns for the S&P 500 index. The only thing I've changed is this last step, which is a filter. And what this filter does is tell R the subset of data that I want to keep. Now you can notice that there's an exclamation point followed by a function that says is.na HPR. This is R's way of understanding that you want everything that is not missing for a particular column. So if you recall before, the SP 500 yearly data had this first row of NAs. I want to remove that. And you'll see how this looks in a second. If I run lines 70 through 78, now notice my SPY data no longer has observations from before the time series begins. Now, there is one thing I want to go back and amend. The data that I called for the S&P 500 is only for 2019 to 2020. So it's not quite the same thing I did before because it's not the full time series. However, this data from 2019 to 2020 is going to lead us to make assumptions about our expected portfolio performance. But with that said, you'll notice there is no row of missing observations. I have a full time series of data for 2020 with my first month's return based off of data from 2019 because I did include 1 month's previous observation. Now if I look back at this filter function, if I were to remove this $sign, this is now going to tell R to keep all observations that are missing for my HPR, which means I should have only one observation in my data set if I were to rerun this. And that's exactly what we get. And the reason I get this one observation from 2019, the end of 2019, is because I did not download anything prior, which means I cannot compute the HPR because there was no previous close value that I computed. However, that's not what we want. I do want to include this exclamation point, so I'll rerun it and proceed to the next step. The second asset that I want to include is a riskier asset. It's for the ticker LRN, and I'm going to use this asset to complement my SPY asset. Everything from lines 82 to 94 are just repeats of what I did for the S&P 500. So if we were to compare the LRN to the SPY object, you'll notice this is same structure, nothing much different, except just different underlying data. Now, because I'm ultimately trying to build up to a situation where I optimize my portfolio, I need to have assumptions going forward, right? So I'm going to base all the assumptions of my future performance upon data from 2020. Now notice I have monthly data here, and if I wanted to, I could aggregate up just like we did for the capital allocation line, where we say, hey, group by year and compute a geometric return. That's perfectly okay. Alternatively, we could use another methodology where we compute an effective annual return for both of these assets based upon the arithmetic averages of their monthly returns. This way is equivalent. It's just a different method, or it's not going to be equivalent per se. It's an acceptable methodology. And in practice, what we would just need to do is justify whatever we use. Here, if I want to use the EAR formula, it's going to be based off of a textbook effective annual rate return, where I'm going to take the averages of some data within a specific objects. Previously, whenever we used the mean function, we included the option na.rm equals true. We can include that here if we want to, but I know I have a full time series of data within my HPR column, so it's not necessarily important for me to include it unless I just want to gain the practice of including this option. And it is good practice, I will say, because it helps us to avoid stupid mistakes whenever we have a potential missing observation. With that said, just to show how this goes, I'm going to exclude it here for lines 98 and 99. And if you look once again at this formula, it's what you may see in a class. It's what you will find if you look online for the EAR formula, where the effective annual rate is just going to be 1 plus some expectation of interest rates or expectation of returns raised to the 12 because the underlying data is monthly, minus 1 because you're going to take whatever this yields and less 1 to make it a return. Because I'm going to reference this data later, I'm going to assign it to an object, EAR-SPY and EAR-LRN. Now if we run these, or just one of these objects, you'll notice R just assigns a value to the name of the object, which is just R's way of saying, hey, this is a scalar. It does not have multiple dimensions, and I can pretty much plug this in anywhere in my script to substitute my need to type 0.43 02855 anytime I need that number. And I'm going to repeat this process in lines 101 to 102, but instead of computing effective annual returns, I'm going to compute standard deviations, or the volatilities of my monthly returns. Instead of using the mean function, we'll use SD, and this will compute the standard deviation of monthly returns. Recall from a previous video, risk has a time component, which we will capture by multiplying the volatility by the square root of the number of time periods that are within the granularity that we're aggregating up to. Because there are 12 periods in a year, I need to multiply my standard deviation of returns by 12. Run both of these. And now because I have a little bit of foresight, I also want to compute the covariance and the correlation between these two assets. To compute the covariance, we use the cov function, COV, and to compute the correlation, we'll use the core function, which is COR. We have to specifically tell R the two objects that we want to compute the covariance and the correlation of. So we'll do this, use a similar syntax as we did for EARs and standard deviations, where I call an object, use a $sign to represent a variable within the object for both SPY and LRN's holding period returns. And now you'll notice I have a different option here, telling it to use pairwise.complete observations. This is the covariance and the correlation functions parallel to na.rm equals true. What these options do is tell R to use only the observations, use only the rows that have non-missing values within both objects' variables. If either one of these, let's say it's an SPY or LRN, are missing an observation for the holding period returns, and I did not include this option, these functions would return an NA, and we don't want that. However, R does have different options. You can tell it to use different data, and each way is great. You just have to be able to justify what you're doing. Well, now we can run these and go down to line 107, where we're going to just reference the risk-free rate for the year 2020 because it parallels the time period over which our equity data comes from. Now, if we pull up the SP 500 yearly objects, our data set, the observation I care about is this last observation in the RF rate column. I can reference it that very specific observation by calling the SP 500 yearly objects, referencing a column RF rate by saying $RF rate, and then using index notation or numeric index notation to tell R to take the 22nd observation within this column within my S&P 500 yearly objects. Depending on your needs, there are easier ways to do this, but I just want you to see that R is versatile. If I run this, you'll now notice that R of 2020 has been assigned a value of 35 basis points, as seen down here in the console, which is the same thing in the SP 500 yearly dataset. If I exit these out and now look at the last section of my data, you'll see I'm now going to build a portfolio based off of my expected returns, and I'm ultimately going to build up to plotting something. Well, what we're going to do is call or create a second portfolio ret object, call it portret2, simply because I don't want to delete or overwrite my original portret objects. And now I'm going to extend my sequences of allocations for my two assets from negative 1.5 to 1.5, or from shorting, trading on margin, one asset to 150%, or going long 150% of another asset. I'm going to break my weights into 10% buckets, rename my first weight item, my first weight column, to LRN, create another column called SPY, which represents the weight I assign to the SPY asset, define a portfolio return or expected portfolio return column as the linear combination of the weights we just generated times the assumptions of returns that we computed in the EAR steps, and compute the volatility of my overall portfolio, which is the weights squared of each asset multiplied by the variances of each asset plus 2 times the weights of each asset times the covariance of the two assets. If I cared about the variance, I could remove this square root function, but because we care about volatilities, we'll take the square root of the variances, which, if you look at the textbook definition of the portfolio variance of a two-asset portfolio, that is a textbook definition. And of course, the square root is the volatility of the variance. Excess returns are computed as before, and Sharpe ratio is computed as before. You can run this step from lines 111 to 117. If I pull up portret2, you'll notice I have some data here that go from negative 1.5 to 1.5 for the weights I assign to LRN, and I also have some weights that now go from 2.5 to negative 5 for SPY. And what this is going to represent is a situation where we have a super risky allocation across these two assets. But one thing I want you to notice is every combination of portfolio weights has to sum up to 1. So although we have a negative 150% allocation LRN and a 250% allocation SPY, the sum of these is going to be equal to 1, which is why every other linear combination also does the same. And of course, the portfolio returns, the excess returns, Sharpe ratios, all of these are data that are going to help us identify what is the optimal allocation of our two assets. Well, thankfully, because we're dealing with a two-asset portfolio, there is an optimal allocation formula. And I'm not going to break down this whole formula because it is kind of lengthy and long. However, if you look up the formula for an optimal allocation of assets within a two-asset portfolio, you'll get a formula that is ultimately a giant fraction, where you take the differences between expected returns and the risk-free rates, and you multiply it by the variances of specific assets, and you include the correlation between assets in a couple of different places. If you want to, you can copy this formula here, or you could type it on your own. Either way, I just want you to understand that you can identify mathematically the optimal points where you're maximize returns for a given level of risk within a two-asset portfolio using this formula. We can also do this in a 3, 4, 5, 20 asset, just an n-asset portfolio, but we have to include a lot of linear algebra after we go outside of two assets. But once you get that point, you can then identify the optimal allocation for the other assets. Now, if I run these two lines of code, if you run and then call these objects, you'll notice R has computed that the optimal allocation for my more speculative asset, LRN, is about 12% and about 88% for my S&P 500 tracking index. Once I get these two values, I can then compute the expected returns for my portfolio, the volatility for the portfolio, my excess returns, and the Sharpe ratio associated with this linear combination of assets. Lines 121 through 124 are really just repeats of everything in lines 114 to 117. If I wanted to combine each of these data points into one, I could do what I show here in line 126, which is the cbind function, which combines each of these objects. It stitches them together column-wise. Or in other words, I'm going to use this to put opt LRN, opt SPY, port ret, port volatility, excess ret, Sharpe ratio beside each other in a left to right fashion, and it's going to make it pretty. Where now I can read this and say if I allocate about 12% to LRN, 88% to SPY, I will generate, or I expect to generate, about 23% return at a cost of 25.6% volatility. I'll have some excess returns over the risk-free rates if things continue with the same risk-free rate, and my Sharpe ratio is about 0.87. We can also use the rbind function here, but instead of stitching things together left to right, it's going to stitch top to bottom. Personally, I think cbind's a little cleaner, but everybody's different here, so do whatever you think is best for you. Now lastly, we can plot the investment opportunity set, which is the combination of each of these portfolio return and portfolio volatility data points on a figure, in addition to the capital allocation line so that way we can visually represent where the CAL intersects the efficient frontier. Well, we know it's going to be something related to this point that I've just highlighted in the console. It should be at an x value of 0.26 and a y value of 0.23, but I want to see it visually. So we're going to use a ggplot set of functions, and we're going to use a scatter plot with the geonPoints function to represent the relation between portfolio volatility in X and portfolio returns on Y. But I'm going to include one more geom, which is geom abline, or AB line, which is just a line with a slope. This geom, this line, is going to require a couple of different options or different inputs. One is the intercept, and the other is the slope. The intercept is going to tell R where to start the line, and the slope is going to tell it where to plot every additional point along the line. Because I'm trying to represent the CAL, I recall that the Sharpe ratio is the slope of the line. And hey, that's convenient. We've already computed the Sharpe ratio. And I also know that the CAL is going to intersect the y-axis at the risk-free rates, because that's the point where you have a guaranteed return with no volatility. So if I combine these 2 points, or these 2 aspects of the line, the risk-free rate and the slope, I'm going to get a line that is associated with my optimal allocation. And just to prove a point, I'm also going to annotate my line by telling R to put in text with a label that says my expected returns are equal to the portret objects, comma 2, or rounded to 2 decimal points, and my optimal SPY allocation is going to be equal to opt SPY, comma 2, and I'm going to put it close to these 2 points in my XY plane. I want you to notice portrets has been defined previously. Opt SPY has been defined previously. Portfol has been defined previously, so on and so forth. The reason why I add 16% to the volatility function, or to the volatility object, is just to push my observation or my text annotation over a little bit. This comes with experience and time. Play around with this on your own to see how things change if you remove this adjustment here. Now everything else are just options. I like the black and white theme. I like to center my title, and my title I'm going to call it the investment opportunity set with optimal allocation. I'll run this, and now wow, looky here. We have the efficient frontier, and we have the capital allocation line, which intersects at one and only 1 point. That 1 point being this guy right here. And it tells us that we should expect to return 23% if we allocate 88% to SPY and 12% to LRN. It looks as if it could be intersecting the line here at that second point, but if you blow this up enough, you'll notice it's going to be deviating by just a little bit. And if we exit this out, and I just want to know what the slope of this line is, we'll see it's 0.87 roughly. And if I open this graph back up, and if for whatever reason you still feel a little uncomfortable about how this line looks like it's intersecting, I want you to notice that that next point here corresponds to the observation where LRN equals to 0.2, which is this, row 18 in the portret2 function, or object, which is associated with a Sharpe ratio of 0.864, which is slightly less than the Sharpe ratio of 0.869. So the slope associated with this, the point where it looks like our CAL is intersecting, is actually going to be lower and non-optimal. There are packages that exist that some very generous users and developers have provided for us that you can download and use their libraries to optimize your portfolios using a lot of different rules, whether it's Sharpe ratios or something else. They can also make this process a lot more seamless. They can incorporate more data. You won't be hard coding a lot of stuff. But with that said, this video was really meant to serve as a way to show you how to do this mathematically and to parallel the things that we're doing in class. As always, if you have any questions, if you have any concerns about any of these steps, feel free to shoot me an email. Reach out. I'm happy to walk you through what we've done. Now, something you'll notice that in this process, a lot of the stuff I do is not perfect, right? It's not necessarily the cleanest. For example, I did overwrite my portret and my port volatility functions, or really my portret object, which I believe I defined up here in the beginning of the video. Right, and in your own practice, you're going to want to avoid doing things like this. But the idea is still the same, and I believe this is a great introduction of how to use R to plot the investment opportunity set and to visually understand what is happening whenever we try to optimize and diversify portfolios. If you have any other questions, as always, feel free to reach out. And look forward to walking you through the next aspect of our tutorial in R.